Okay, let's get right into it. Today, we're not just going to talk about motion. We are going to crack the code on a real GCSE physics exam question. We're going to pull it apart piece by piece so you can see exactly how these concepts are tested, and more importantly, what a perfect answer looks like according to the mark scheme. So here's the big question, right? How do you look at a bunch of lines on a graph and see the full story of a train's journey? We're going to learn how to read it, not just as data points, but as a narrative, where it speeds up, where it holds steady, and where it finally breaks. And here it is. This is our puzzle. This one graph holds all the clues we need. Every single answer we're about to figure out is hiding in plain sight on these axes. So let's jump in with the first part of the question. First up, the exam wants to know the distance the train covered in the first 600 seconds. That's the entire period where it's accelerating and then cruising at a constant speed. Now, before you even think about grabbing a calculator, there's a golden rule you have to know. On any velocity time graph, the distance traveled is simply the area under the line. That's it. It's one of those fundamental physics principles that will score you easy marks if you remember it. So, how do we find that area? Well, you could use the formula for a trapezium, sure, but honestly, it's often way easier to just split this weird shape into two simple ones we know and love, a triangle for the acceleration bit and a rectangle for the constant velocity part. Then we just add them up. And here, you can see the official mark scheme actually lists both methods. This is what the examiners are looking for. You can use the trapezium formula if you're comfortable with it, or you can do what we just said, calculate the triangle and the rectangle separately. Notice how both methods get you to the exact same place. It's good to know you have options. So, there's our final answer, 26,600 meters. To put that in perspective, that's more than 26 kilometers, or about 16 miles, all in the first 10 minutes of its journey. Okay, let's move on. Now we're shifting gears from a calculation to an explanation. We need to look at the second half of the train's journey, when it starts braking, and explain what's happening with the braking force just by looking at the graph. Okay, so zero in on the part of the graph after the 600-second mark. What do you notice? It's not one smooth, straight line, is it? It's actually two different straight lines connected. The first part is steeper, and the second part is a bit shallower. That little detail is everything. And this is the logic that gets you full marks. First, you state the obvious. The gradient of the line tells you the deceleration. Second, you point out that the gradient isn't constant. It changes. And third, you connect it all together. Since force equals mass times acceleration, and the train's mass doesn't change, a changing deceleration must mean the braking force is also changing. It's a perfect chain of reasoning. All right, back to the numbers. The next question asks us to find the maximum deceleration. So we're looking for the exact moment the train was slowing down the fastest. So where do we find that? Well, we just said it. The gradient is the deceleration. So finding the maximum deceleration is just a fancy way of saying find the steepest part of the downward slope. And just by looking at it, that's clearly the first part of the braking, between 600 and 700 seconds. And here's the calculation, straight from the mark scheme. Remember, gradient is just the change on the vertical axis, the rise, divided by the change on the horizontal axis, the run. Here, the velocity drops from 56 down to 20 over a 100-second period, so that's a change of 36 divided by 100. And that gives us our answer, 0.36 meters per second squared. That number tells us the train's deceleration at the very moment its brakes were being applied with the most force. Okay, time to level up. The next part throws a brand new scenario at us with a different train. This is a really common exam trick, designed to see if you can take the principles you know and apply them to a completely new problem, often by combining a couple of different equations. So here's the setup. We've got speed, we've got braking force, and we've got mass. The mission? Figure out the braking distance. This is going to be a two-step problem no matter how you slice it. And just like before, there's more than one way to get to the answer. The mark scheme shows two valid paths. The first uses the classic force and motion equations. The second, which is pretty cool, uses the concepts of energy and work done. Let's quickly walk through both. Okay, method one, using forces. First, you rearrange F equals ma to find the deceleration. Easy enough. Then you plug that value for a into this big equation of motion, v squared minus u squared equals 2as. You just pop in the numbers, rearrange to solve for s, the distance, and you're there. Now for the energy method. This one's really elegant. The basic idea is that to stop the train, the work done by the brakes has to be equal to all the kinetic energy the train had to begin with. So, you calculate its initial kinetic energy, set that equal to force times distance, and solve for distance. And boom, you get the exact same answer. And there it is, 1,600 meters. It doesn't matter which path you take, the physics leads you to the same conclusion. That's 1.6 kilometers, basically a full mile, for this train to come to a complete stop. It really gives you a sense of the massive forces and energies we're dealing with. Okay, for the final part, the question brings it all back to the real world. This is where you have to show that you don't just know the equations, but you understand what they actually mean for our safety. And the question is simple and direct. What does alcohol have to do with stopping distance? This takes us out of pure physics and makes us connect the science to human biology and reaction times. And here is the perfect, concise answer that the examiners are looking for. It's a simple three-step chain of logic. 1. Drinking alcohol makes your reaction time slower. 2. A slower reaction time means you travel further before you even hit the brakes. That's the thinking distance. 3. Therefore, the total stopping distance, which is thinking distance plus braking distance, gets longer. Simple, logical, full marks. So there you have it. We've completely dissected a complex exam question, from reading graphs to doing multi-step calculations, all the way to real-world safety. It really just leaves you with one final thought. We've used a train as our example, but where else do these exact same principles of motion, force, and energy play a critical role in our safety every single day?